Hello, this is Blake or Sterling, depending on what you want to call me. Doesn't matter. Pretty much this is going to be homework 7, and we're going to talk about sums of geometric and telescope series. I have 2 problems here from the homework that I'm going to explain, and hopefully you understand why after all of this. So first off, we have question 18, and it says use the formula for the sum of a geometric series to find the sum. Pretty much what we have here is, and I'm going to explain these later and I'm going to prove them, but we have 2 functions. S sub n is equal to a over 1 minus r, and then we also have the s sub n is equal to a minus r to the nth divided by 1 minus r. Now, these can be like confusing, like which one do I use and which one in certain cases and why are they like this and things like that, but we're going to make this all clear. So how do I start out the problem? What I start out by doing is writing the first few terms in this series, right? And so to do that, we just plug in the first term. So the first term with like a sub 1, we're going to plug in n is equal to 2. So we go down here, and once you plug in n is equal to 2, you have negative 3 to the second power, so raised to the second power, and you have a 9 times 7, so then you get 63. And then you have 5 raised to the second power, so you get 25, right? So our first a sub 1 is going to be equal to 63 over 25. Now I want to point out that in order to use these equations right here, then we're going to need an a value and an r value. So, well, what is a and r? What is a and what is r? I have it right here. A is going to be your first term in your sequence or a series. This is a series, and I'll explain series and sequence because they're confusing, but I'll explain it later. So this is going to be your a because this is your first term in your sequence. Notice that when we plug in n is equal to 2, n is equal to 2 is our first term, so this is equal to a. It's not you plug in n is equal to 1, n is equal to 0. We're starting with n is equal to 2, so that is going to be your first term. So your first term is a, your first term is 63 over 5. Now, second question, what is r? R is going to be the factor that you're multiplying by. So let's continue writing out this series, or this, series sequence. Let's continue writing, well, this, when you're adding them together, it's called a series. So when you're adding them together, it's called a series, so we're going to continue writing out this series. Remember, this is the shorthand way of doing it, and then this is going to be the longhand way of doing it. So I'll just annotate that up here. Okay, so now the second term, a sub 2, the second term in this geometric series is going to be when n is equal to 3. So now once you plug in 3 to your n, then you're going to get this, 189 over 125. And so this is pretty straightforward. You plug in n is equal to 3. You plug in 3 into this, so it's going to be 7 times negative 3 to the third power. And then you're going to do 5 to the third power. And so you get negative 189 divided by 125. All it is just plugging in so far. Now, once you plug in 4, then you get this number right here, 567 over 625. Now, when you're doing these types of problems, all you really need is this first part, pretty much. You only need to write out the first 2 terms, and that'll give you the a and the r. However, just for the sake of this tutorial, then I'm going to just write out the 3 terms so that you can see what we're going to do. So we know what a is. A is our first term, so that's going to be 63 over 25. Now we have to figure out our r. Now, the whole reason that this is a geometric series is based off of the fact that we can multiply by a factor each time. So this next one, a sub 4, is going to be multiplied by r. So multiplying a3 by r to get a4. So I'm pretty sure you've seen in lecture, maybe they say a2 over a1 is equal to r. This is a very simple equation, but just to make sense of it, you just have to do a times some number of r is going to get you to a2. Likewise, if you look at a2 times some number of r, some factor, is going to get you to a3. Now, in order to solve for r, then of course you just do r is equal to a2 over a1. And so r is equal to a3 over a2. So we need to figure out what r is equal. And how do we do that? We take this number, which is a2, so we'll write it here, a2 divided by the a1. So divided by this. And so when you're dividing them, then you're going to get negative 3 over 5. And you can test this. And I know when you punch it into your calculator, or you can solve it by hand, then it may seem confusing. Is this really right? You can check it. 63. So this is going to be a1 times 3. Say over 5, negative 3 over 5. So when you do 63 times 3, you get 89. And you do 25 times 5, you get 125. And this is minus, so then this is going to be a minus sign. Now, there you have it. That's your r right there. Your r is going to be negative 3 over 5. Now, I said that you're able to just look at these first two terms and get your r, and that's true, but let's just test it. Negative 3 over 5, and we're multiplying. You take a negative number times another negative number. Negative times negative is going to give you the positive. And 189 times 3 is going to give you 567. 125 times 5 is going to give you 625. So you can see that this r right here, this r is the same thing as this r. We multiplied by negative 3 over 5 right here to get this. And we multiplied by negative 3 over 5 to get this. This is the reason why it's called a geometric series, because of the fact that we can multiply by this r. Okay, cool. We got that out the way. And that's going to be important when it comes to proving the formula later. So, well, we have everything that we need. And now the question is, which equation do we plug it into? Well, I said that we use this equation when we have an infinite sum that we're calculating, right? And I guess we can go behind the reasoning behind this right now to solidify why we use each equation. So imagine if we have a jar. Oops, that's a pretty big jar. Imagine if we have a jar and there's a sandbox right here. So this is the sandbox. And every time I go to the sandbox, I'm going to go and take back some sand. And let's say that sand is represented by, say, for example, 1 package of sand. Now, if I'm going back and forth, and I'm bringing, and my sand packages are getting bigger and bigger and bigger, eventually, if I go back and forth, I'm going to have an infinite amount of sand in this jar. So that's representative of something if we had a sequence or a series like, so if I'm going back and forth, boom, 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 boom. At first, I'll show you here, I'll bring 2 packets of sand. And then I'm going to bring 4 packets of sand. 1, 2, 3, 4. And I'm pretty sure you get the idea. And this is if R is greater than 2. So every trip that I make, I'm bringing back more and more packets of sand. So if I make an infinite amount of trips, then I'm going to have an infinite amount of sand, right? Now let's look at another example. Say, for example, the geometric series was 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus 1 over 32. You can see that our R here, right here, here, each time we're going to be multiplying by 1/2. Multiply by 1/2, and you get the point. So this is representative. Say, for example, a pack of sand looks like this. So what I'm going to do, or say a half a pack of sand looks like this. What I'm going to do is I'm going to put half of a package of sand in this jar. Then I'm going to go back to the sandbox, come back, and I'm going to bring half of this half of a package of sand. So if the first package of sand was this big, now I'm going to bring back some sand that's only this big. So I'm going to bring back this sand. Now, here, actually, let's keep that there. And now I'm going to go back, come back, and now I'm going to bring sand that is only half as big as that last bit of sand. So I'm going to take this ball of sand, and I'm going to put it in the jar. And you get the point. Pretty much, I'm going to have, say, for example, some sand. And if I make infinite amount of trips, eventually I'm going to be putting in smaller and smaller packs of sand, right? Eventually, I'll even have a grain of sand. And then the trip after that, I'm going to have half of a grain of sand. So you can see that this jar is never going to completely fill up, right? And so eventually it gets to a certain amount at which the sand that we're adding is pretty negligible. If I tell you that we have, say, 5 pounds of sand, if I add half of a grain of sand to that 5 pounds of sand, then it's still going to probably just be 5 pounds of sand, right? So let's look at this here. Now, keep in mind that this is representative if R is less than 1, right? So in this case, R is 1/2, so this matches. What I put over here is an infinite when R is less than 1, okay? So when R is less than 1, we're going to eventually get some amount of sand. Even though we're not going to fill up the whole jar, this is still an amount of sand, okay? So you may ask, well, why is it just not R greater? Oh, I'm sorry, this is supposed to be less than. Why is it not R greater than 1? Well, as we said in the first example, if we have R is greater than 1, then we're going to have infinite amount of sand, right? So that's a case where it'll diverge. If R is greater than 1, then you're going to be adding infinite amount of sand. And so if you make infinite trips to the sandbox, and each time you're making a trip, you're bringing back more and more sand, then you're just going to have an infinite amount of sand. However, if you're bringing back less and less sand, so R is less than 1, if R is less than 1 here, then you're going to eventually get a certain amount of sand. And for the difference between these two equations is you would pretty much use this one when it's finite. Now remember I said that when you're bringing back half of the amount of sand, or if you're bringing back less and less sand, you're still having a sum. So That's representative of this. This is the number of trips that you'll take, pretty much, right? And if you're bringing back more and more sand, if you have a finite amount of trips, then you're still going to have a final amount, even if you're bringing back more and more sand, right? So hopefully that makes sense so far. Now we have our A. We have our A. Oops, that's not an arrow. We have our A and we have our R. So all you have to do is just simply plug in at this point. A is equal to 63 over 25 divided by 1 minus negative 3 over 5, right? So you can rewrite this as 63 divided by 25 over 5 because that's equal to 1, common denominator, plus 3 over 5. Then you get 63 over 25 over 8 over 5. This is the same thing if you're doing something divided by a fraction. This is the same thing as 63 over 25 times the reciprocal of the fraction underneath times 8. And then so once you do this, and let's get our calculator here, 63 times 5 is going to give you 315. And 25 times 8 is going to give you 200. So this is the final answer. We're going to put this up here and match it with the correct answer. So in summary, what you want to first do is write down the first two, or let's say first three terms to be safe. First three terms. And so that's what we did. We have first term, second term, third term. Second, you want to look at R. And the reason why I say look at R is because we see here that R is, and remember, this is the absolute value. So negative 3 over 5, we're going to look at this as 3 divided by 5. And we're going to say, okay, is this less than or greater than 1? Or hold on, let's see, 1. Is this less than or greater than 1? Well, this is going to be less than 1. And so when it's less than 1, then we're going to have an amount that we're going to eventually get to if we're making that infinite amount of trips right here. This is the infinite amount of trips. Okay? But if R is greater than 1, say R is 2, and we're looking at the absolute value, or even let's make sure we understand here. Let's say R was negative 2. Negative 2 is technically, or it is less than 1. However, this is why we're looking at the absolute value of negative 2. And the absolute value of negative 2 is indeed less than 1. I mean, is greater than 1, I'm sorry. Greater than 1. And so we can look up here when we have this infinite amount of trips going back and forth, bringing more and more sand, then we're going to eventually have infinite sand, and the series is going to diverge because you're not getting a finite amount of sand. You're going to get infinite amount of sand, right? So that's why we look at R, because if you look at R and the absolute value of R is greater than 1, then you're already done with the problem. Let's look at the third step. So the next step after that is identify A and R. Or sorry, I shouldn't write this capital. I'm just write it lowercase. Identify A and R, and you know A right here is going to be your first term, and R is going to be your factor. that you're multiplying by each time. Okay? And then fourth step, plug in. Okay, so that's pretty much how you do this problem, and hopefully that gives you some intuition on how to do this problem. Now let's take a break from geometric series and let's look at telescope series or telescoping series, or however they want to call it. Now I let these answers sit here because this is pretty much self-explanatory. You're going to take n and you're going to plug it in to here. So you're going to have an a sub 1 plus a sub 2 plus a sub 3. And so this sum is going to give you, right here, this sum is going to give you 3 over 10. When you do this plus a sub 4, this sum is going to give you 1 over 3. And so you can test that for yourself. It's pretty much just plugging in numbers and just adding them together. Now, are we able to, this is a good question. If we have this finite amount of sums, right, and we're able to plug it in to n right here, we plug in the 3 to the n, then are we going to get this number? I'm not certain, but because obviously I'm not an expert, I'm just showing you how to do the homework, but I'm not an expert. However, I believe we won't because, well, what would our r be? And once you write this out, then it's gonna I think it's gonna be pretty hard to find an r because it's not a geometric series, right? So, what do? We want to figure out pretty much when we add this up infinitely. Well, I feel like the first step to a lot of these problems is write out the series. Or I'd say first terms of series. Okay, cool. So now we're going to write out the first terms of the series. Now, let's look at this. We plug in 1. So 1 plus 1, we're going to get 1 over 2 minus 1 over 3. Now, yes, you can find a common denominator and, subtract them. But you don't want to do that for this because it's going to be hard for you to see what we're going to do. The next term, so this is, say, a sub 1. Now we're going to look at a sub 2. Or, actually, I don't want to put a sub 2 or whatever. I'm going to just put first, because the sub 2 and sub 1 may get confusing. So this is the first term. Remember, the first term, you're starting with 1. So you're plugging in 1. 1 plus 1 is the 2. 1 plus 2 is the 3. And we minus. Okay, cool. Next one, 2. So second is the second term. Now, I just want to make sure that this is clear that this 1 does not correspond with this first term. And the n equals 2 for the second term does not correspond with the second term. We saw that in this first problem. The first term ended up being with n is equal to 2. And the second term ended up with being n is equal to 3. So this 2 and the second term, or whatever it is, they do not correspond with each other. Okay, cool. Hopefully I made that clear. Now we plug in 2. So we plug in 2 to the n, and we plug in 2 to n, and we plug in 2 to n. So you have 1 over 2 plus 1, which is 1 over 3, minus 2 plus 2 is 4, so 1 over 4. So essentially we're going to keep adding this, and now we want to look at our n minus 1 term. And so this is going to be our second to last term in the series, okay? And the reason why it's n minus 1 is because if we look at it, our nth term is when we simply plug in n. So yeah, is when we simply plug in n to the into the series thing, right? So when we plug in n to the series, then we just have what we really started with. 1 over n plus 1 minus 1 over n plus 2. Cool. Now we're going to add. What we want to do is we want to take our series and plug in the n value that we have here. What we've been doing so far is plugging in n is equal to 1, so we plug in 1. When n is equal to 2, we plug in 2. So this is n is equal to 1, n is equal to 2. This one, n is equal to n minus 1, and this one, n is equal to 1. I'm sorry. Whoa. N is equal to just n, okay? And so then that's why we plug in n. So when we have 1 over, I'm going to put a space for now, minus 1 over space plus 2. Now, what we've been doing is we've just been plugging in values to these, right? So this time is no different. We're going to plug in n minus 1. N minus 1. And you can see what you get here. Oops. What you're going to get is you're going to get 1 minus 1 plus 1. It's going to get 1 over n. Minus 1 plus 2, you're going to get 1 over n plus 1. Now, why is this called a telescoping series? Well, I think this is the satisfying thing or something that the teacher's been hyping up, like, oh, the series is so satisfying, yada, yada, yada. You're basically just taking this 1 over 3, this negative 1 over 3, plus 1 over 3. These two are going to cancel. This 1 over 4 is going to cancel with a 1 over 4 here. We're going to erase this. We said that this thing right here that we had is equal to this thing. We're just making it simpler. We're going to put this here. Going to put our lovely brackets around it. So what you have is, here we go. You're going to have this cancel with something in there. And the reason why I wanted to write this term is to show you that at the very end, we're going to have minus 1 over n plus 1 plus a positive 1 over n plus 1. These two are going to cancel. So at the very end, let me give myself some space here. At the very end, all we're going to have is this term and this term. So let's put that together. 1 over 2 minus 1 over n plus 2. Now remember, we have infinity up here. So n is approaching infinity. So we need to calculate this thing, but the limit as n approaches infinity. Well, this is just 1 over 2 minus, we need to say, what does this do as n approaches infinity? So the denominator is getting really, really, really big. So, if you just imagine this on a graph, you're taking a number and you're dividing it by a big number. Now you're going to take the same number, and if you multiplied it by another big number, then it'll go up. But you're multiplying it by you're dividing it by a big number, so now it's going to be smaller. And as you can see, it's going to be smaller, 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 smaller. As n approaches infinity, then you're going to approach 0. And here, my bad, I don't want to write 0 right there. Let's say 0. So you're going to approach this y value of 0. So this thing approaches 0. Well, what do you have here? You have 1/2 minus 0. 1/2, well, I'm not going to write it again, but 1/2 minus 0 is just 1/2. And let's check. That's what we have there. So that is correct. So now hopefully you understand the reasoning behind the telescoping series and the geometric series. Now this is one last thing, and we're going to take these two formulas and prove them. Now, you don't need to necessarily do this on every, let's say, how should I put this? I don't think we're going to have to do this on every midterm and on the final and prove it, or maybe they'll make us prove it, but I'm not sure. But it's always good to know why things work the way they do. We have S sub n. It's a geometric sequence, right? So now we're going to get some clarity on what sequence, series, yada, 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 right? So we have our first term A plus AR plus AR squared plus AR cubed. Let me write this square better. Plus AR to the fourth, dot, dot, dot. Gonna eventually have AR to the n minus 1. Now, let's break this down. Oh, I'm sorry. We're gonna... This is to, let's clear this up right now. Sequence, series, we always hear about sequences and series, right? Pretty much, oh, hold on. So let me just write this. Pretty much this thing right here is called a series. This thing right here, this is still a series right now, but we're just going to change it. We're going to take this, take out the plus signs, replace them with a comma. Now, you may ask, why did I do that? Well, I don't know why I did it either, but the mathematicians and the fancy math people call this a sequence. And so when you think of sequence, think of list. And so you can think of the commas, you're listing out the different numbers, right? So this is a sequence, this is a list. And I'll keep this, actually here, how about this? I'll move this down, keep this right here, up here, and I'll have that there. Oops. Come back, okay. So I'll have that right there. Now, we want to prove this. Eventually we're going to get the A over, 1 minus R. And we're going to get the A, what is this? 1 minus R to the N divided by 1 minus R. I realized that I made a terrible, terrible mistake. Originally, I had this A minus R to the N, but I realized that it should be A times 1 minus R to the N, and we're going to see that in the proof. So eventually, we're going to get these two equations, okay? Sorry about that. So discard what you were saying, discard about the A minus R to the N over 1 minus R. This is not the correct formula, okay? Cool. My apologies. So this is the first time I'm doing these math explaining videos, so sorry about that. Anyway, we move and we say that S sub n, we're going to take another S sub n. S sub n is going to be equal to this thing. Boom, boom, R squared plus AR cubed plus AR to the fourth, dot, 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 ARN. We need some space. We need some space away from math too sometimes. So we have these two things, and obviously S sub n is equal to S sub n. Now what we're going to do, well, before we do that, actually, let's make sure we understand this first thing. This is a geometric series. We're adding them together, so we're adding them together. And this is the thing about the r. We multiply it by r, and when you multiply by r again, then, oops, whoa, why did I write that? Multiply by r, you get r squared. So then you multiply again, you get times r, so r cubed. So you see why we're multiplying by r in each term. All right, let's look at the next part. Now what we're going to do is some mathematicians were pretty much like playing around, and they decided, okay, we're going to multiply this side by r. Now all of these are going to be multiplied by r. So this is going to be r. Oops. It's going to be r squared, r cubed, r to the fourth, r to the fifth, right? And so once we multiply, we're just increasing pretty much the powers of r. And now this one may be a little tricky, but I want to break it down to make sure we understand. If we have x to the third times x, you're going to get x to the 3 plus 1. This is x to the first. You can see that. So now when we have r to the n minus 1 times r to the 1, you're going to get r to the n minus 1 plus 1. So essentially, right here, we just have r to the n. I just want to make sure that's clear for everyone too. So now what were we going to do? We're going to subtract these two equations from each other, because we can do that. So I'm going to write it like this. I'm going to take this over here. We're going to subtract them. Now, I mean, you can still, like, you can add them and say you multiplied by negative r, maybe, but we're just going to just subtract them and stay consistent with what we did in lecture. So I know this says RA. You could still write this as AR, just to be clear. And what we can do is we can see that when we take this and subtract, and let's break this down. I was a little bit confused about this when I first saw it too. But if we have 1 plus 2 plus 3 plus 4 minus 2 minus 3 minus, I'm going to just say that, right? And so once we have that, then this plus 2 and minus 2 will cancel. This plus 3 and minus 3 will cancel. Oops, sorry. And then let's say this has like, ooh, wow, this iPad's acting up, okay. Minus 4 and then minus 5. Then these 4s would cancel, and we're just left with 1 minus 5. Okay, so we see how that works. Now we're going to do the same thing here and subtract all the infinite amount of terms, and we're going to see something interesting. This is going to cancel out with this. This is going to cancel out with this. Cancel, 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 cancel. And a to the, what is this? AR to the n minus 1 is going to cancel with an AR to the n minus 1. Okay? So what do we have here? We have, and I'll write it bigger, S sub n. Okay, maybe that's a little too big. Let's write it slightly bigger. This is pretty shocking math discovery. S sub n minus r S sub n is going to be equal to the things that we have left. A, and then you have your minus AR to the n. So A minus AR to the n. Now let's clean this up a bit. We could factor out the S sub n. So S sub n, 1 minus r. is equal to a, factor out the a, 1 minus r to the n. Now we want to see what s sub n is equal to. S sub n, just divide by the 1 over r, divide by 1 over r, right? And what you do to one side, you have to do to the other, so then that's why you're going to see a 1 minus r to the n divided by 1 minus r. Okay, cool. Hooray, we found our formula. And this thing looks exactly like this thing. But you're asking yourself, okay, well, what about this thing? Now, this equation, let me be careful what I'm saying here. This equation right here is to find the sum when we have a finite amount of points. So if we go back up to our problem, here we had an infinite amount of points. But let's just say we replace this with 5. Well, we know how to do this. We just add them up. We figure out what the first term, the first, second, third, fourth, and fifth term would be. And then you're going to add them up together. And then you get this thing pretty much. That's your answer. A quicker way to doing that, say, for example, this is 1,000. Now go ahead and calculate, write down 1,000 sums of this, and then add them together. It'll probably be there for a while. So if you want to be cool, then just use this formula, right? Now this formula is going to work for when you have the finite amount. So remember, this is for the finite amount. Let's think of our sandbox example. This is going to be the number of trips that we're taking to our sandbox, okay? Sandbox. Cool. So that's the finite thing. Now when we have an infinite amount, this is when r, absolute value of r is less than 1, or absolute value of r is greater than 1. Okay, so yeah, that's that. So you're going to add it up, and then you're going to get a number. You're going to get a numb. There you go. Okay, actually, let me keep that r there. So now this one is going to be for when r is less than 1. Okay? Absolute value of r is less than 1. So this is when you have n approaching infinity. Now we already discussed, if we go to the sandbox, come back, and we make infinite amount of trips, and each trip we're bringing back more and more sand, we're going to get infinite amount of sand. In this case, your answer is equal to infinite amount of sand, infinite amount, and so therefore it diverges. Diverge. Okay? But what if you want infinite trips, however, you're bringing back less and less sand, right? Well, I don't know why you would make that many trips to a sandbox to bring less and less sand. I question what you're doing with your time at that point. However, we're going to look at that case. Let's say r is something less than 1. It's 1/2. We're going to pretty much, my alarm. We're going to pretty much take this formula right here and calculate the limit as n approaches infinity when, under the condition, absolute value of r is less than 1. Keep writing this down. So let's say, for example, r is equal to 1/2 and to the n. The limit as n approaches infinity of this is going to equal 0. Now you may ask why this is. Well, you have a half. So when n is, let's just look at this. So n is going to keep getting bigger. And so when it's going to start at 1. So 1 over 2 is 1 over 2. 1 over 2 to the power of 1 is 1 over 2. 1 over 2 to the power of 2 is going to be 1 over 2 times 1 over 2, which is just 1 over 4. N is equal to 3. 1 over 2 to the power of 3. So 1 over 2 times 1 over 2 times 1 over 2. You're going to get 1 over 8. So you see that this denominator is getting larger and larger and larger. And when we have one number divided by pretty much an infinite number, an infinitely large number, the limit's going to equal 0. So what do we do here? Well, this whole thing, and I'll write it in another color, this thing is going to be 0 when, keep in mind, r is less than 1, okay? So now we're going to have 1 minus 0. 1 times a is just a, and we're going to keep the same thing. 1 over, it's over a over 1 minus r. And I believe that's pretty much it. That's pretty much all there is to say about the sums of geometric and telescope series for homework 7. Hope you enjoyed. Let me know. Let me write this bigger, better ink. Let me know if any questions. And thanks for watching, and hopefully this helped. Let me know if this helped in the Discord. Please give me feedback. Thanks.